All right, good morning to those of us in the US, good afternoon, evening to those around the world. So this is kind of a fun side project we've been doing that my master's student Julio Chavez has been working on for the past year or so. This is an experimental investigation using surface PIV to try to measure volumetric discharge in an open channel. So our motivation, it seems like we're all on the same page here, so I can hit this one pretty quickly. It is, I think, as we all know, impossible to ever, with 100% accuracy, measure what is the actual volumetric discharge in a natural stream with, changing bathymetry that varies heavily in space and in time, where we have recirculation or we have all sorts of obstructions. It is impossible to really know what that volumetric discharge is. A lot of our present methods that are historically used are fairly obtrusive, but obviously there's a strong push here to develop better remote sensing. In particular, for this one, we're looking at pretty low cost remote sensing, as you'll see. In Texas in particular, our waterways, a lot of them are either bone dry or they are flooding. And so here we're very interested in understanding, rapid responses. What is the water doing in response to a very large and sudden storm event? And in particular here, a big thing is looking at how does that contribute to bridge scour and our bridges washing out? And can we develop systems to be able to predict this in really short time spans? And so we're diving into this to look at surface PIV to try to address some of these problems in our natural systems. The approach for using or for measuring stream discharge, we can say it is just if we discretize our stream into various subsections, if we know the depth average velocity for that little slice of our stream and multiply that by our cross-sectional area, we can multiply that and get our volumetric flow. The more we discretize, the more accurate it is, but the more labor intensive it is to get in there and do these measurements. So can this be done remotely? So there is an extensive background in this. I will highlight the work of Erica Johnson, who I believe is going to be presenting some of her work tomorrow. But just to point out, so Erica and I, we are both Johnsons. We were both at Cornell at the same time in the same lab. And so there are several wonderful Johnson and Cowen papers from this time. All of the ones on surface velocimetry are hers. We have just picked this up in my new lab as like kind of a fun side project because we have a fun facility to do it in. But all of the credit for the background I will attribute to Erica's work. So in her PhD work, she had a really nice wide indoor channel and was using surface PIV and some other techniques to see how can you predict the bathymetry when you are not doing in situ actual, depth measurements, and then can you measure a volumetric discharge just from surface measurements alone? And I remember Erica worked extremely hard to get seating right and the lighting right, because working with visual images and just purely optical based measurements with natural lighting or ambient lighting was extremely challenging. And she was really trying to figure out, if we take signatures of the turbulent features on the surface of the flow, how can we learn something about the three-dimensional dynamics just from surface turbulence? If I can summarize that in a brief nutshell of her work. So what we wanted to do after her lab studies, I then moved to the University of Texas at Austin, where we have this very large outdoor flume. Basically wanted to see, could we extend some of Erica's work to the outdoors and ultimately aim to get into natural systems. But for right now, we are still keeping things pretty fundamental in a large rectangular flume. This is a concrete channel about 5 feet wide, approximately 3 feet deep, 130 feet long. This thing is huge. The water that feeds this is coming from a reservoir, which we're saying is natural. If you think of like those big circular reservoirs at a water treatment plant, that is kind of what we have feeding our system. So there is all sort of organic matter in there depending on the day. And we are able to generate some pretty decent flow rates through this. So here is our testing section. Our instrumentation here, the focus is our surface PIV. So up On the upper right-hand side, you can see we have a camera facing downward above the channel. This is an $800 pretty cheap, you know, in our standards camera that is looking down on the surface. So this is what we're using for our surface particle image velocimetry. At the back of our two-dimensional PIV field, we also have a Nortek Vectrino that lets us measure at a single point all three components of velocity, so we can look at the depth variation of our velocity profile. I will mention, I'm not really presenting it in this talk, but in our left cartoon, you can see we also use these tilt meters. These are made by Lowell. These are really clever, also pretty inexpensive devices to measure velocities and discharges. When we used them, unfortunately, we got really different results between what the tilt meters were giving us was the velocity and what the ADV and what the PIV was telling us. I think we might have just gotten an unlucky batch. Something was off with the calibration. So I am definitely intrigued to kind of keep playing with these tilt meters because it's just basically a plastic rod and it just takes advantage of buoyancy, and at whatever angle this thing is leaning in the flow, you can then back out what the velocity would be. So these are great, easily deployable field instruments, but I will not be talking about them today. So let's talk first about the PIV. So this is a downward facing surface particle image velocimetry. We have these little JAI cameras. It's a 5 megapixel camera that just records continuously. And so we were sampling from 30 to 60 hertz. And in PIV, we need surface matter to be able to track as a function of time and hopefully have some sort of decent spatial resolution. There are days in this channel where we have tons of bubbles and maybe leaves or algae or different things coming through that we can track. But as you can see on the left, there's also a lot of days where the water is really disappointingly clear. And so we were looking at artificially seeding the channel with either wood chips because we can easily skim them back off the surface. And if a few of them make it through, it doesn't really matter. And also biodegradable glitter, which you can see on the upper right-hand side. And so obviously these give us very different spatial resolutions. The glitter much finer, the wood chips are much larger, but we're kind of playing with these to see, you know, just a natural illumination. Can we get some sort of useful data out of this? All right, so we are working outside, which means we can't really control the lighting very well. So we have a lot of images that have horrible reflections and shadows. Our free surface is not perfectly flat. And so these images are kind of a nightmare to work with. I had many days where my students were just asking me to hold cardboard and try to block the sun. So, you know, I did it to support the research, but, you know, this is not sustainable to have to depend so much on just being out there at the right time of day, et cetera. And so one of the things my student has worked a lot on is using lots of different pre-processing and binarization techniques to see, can we highlight the particles that are in the flow any stronger? And we've been getting at that through binarization. So on the right, this adaptive binarization scheme he worked through, we see much clearer, more distinct surface particles that then we can put through our PIV algorithm. Obviously here, there's still a big gap in this flow. We also saw lots of clustering of particles. And so even though we are artificially seeding this, it is really hard to get a uniformly distributed, well-seeded, you know, crisp images that we can analyze, but we are doing our best with it. So you can see this really helps this really helps our image to go through these binarization schemes. Still not perfect, but at least something that we can try to analyze. So, oops, I got stuck. Oops. So we can run this through our PIV algorithm. I know you've seen several things about this morning, but basically we can track, you know, the image on the left is showing us the black markings show us where were our tracer particles at time A. Our white shows us where were they at time B. And then we can develop the fully two-dimensional velocity field that captures the flow. This was one of the better images, but again, we have many that are much more sparsely populated. And so we might get really large sections where we don't have, either we don't have vectors or we don't have high confidence in their accuracy. So the quality of these really varies depending on our lighting and our seating. All right. The ADV we have in here also because we need to know the depth average velocity currently with this method. We're using a Nortrek Vectrino, which I believe these are already out of production or almost out of production. So these are vintage instruments. For the experiments I'm showing today, these were collected just at 25 hertz, but ideally we would go a lot faster to actually see some of the turbulence in this. This gives us a point measurement. Our measurement region for this is just at the downstream edge of the PIV field of view, so that hopefully we can see some sort of similarities in our samples. And this lets us look at the turbulent boundary layer within our flow and not just at the surface. All right. So this gives us velocity profile, so we can see how this is structured with depth. And then we can ultimately determine the bulk depth average velocity. And our last measurement technique for this is we have a weir in this flume. We don't have weirs in natural rivers and systems, but in our channel we do. So we are able to measure the flow over this weir and consider that as our ground truth to actually, to be able to calculate Q, to calculate our discharge from our PIV and from our ADV, but then be able to compare it with our weir measurements to see if we were on the mark or not. So one of the main contributions of Erica's PhD work was then, as we said, kind of harvesting that turbulence at the surface and seeing how can that be utilized to infer our flow depth and our bathymetry so we can calculate the volumetric discharge. So I won't go through all the details of this, but I would be happy to, and I'm sure she would be as well, to go through how this works. But our integral length scale, what this tells us is the size of our largest characteristic eddies, in this case on the surface of the flow. So we know we have these rotating eddies that are moving downstream as the bulk flow also is carried downstream. And so does the size of, or how is the size of those eddies essentially connected to the bathymetry? We can imagine those eddies are limited by geometry. And so that is going to let us correlate our integral length scale or our size of our eddies with our actual flow depth so that then we can, develop this a little bit further. So I'll just go through this part very briefly, but if we have our flow direction, in this case, going from top to bottom, this is just downstream our channel. Our red velocities here are our downstream velocities, our blue are our cross stream. And so we can calculate the integral length scale is the integral of our normalized spatial autocorrelation. So if we have, an eddy that takes up this entire span, we're going to see a different correlation than if we have really tiny eddies that do not have a strong spatial correlation. So we can calculate the integral length scale or kind of our eddy size using both the downstream and the transverse velocities, and then see how these two different integral length scales compare to our flow depths. All right, so on the left, we have our downstream velocities. On the right, we are doing this from our transverse velocities. This is a big difference from Erica's result, where on the left is kind of what we expect to see, is that as we have an increase in water depth, we also have an increase in integral length scale, which we see on the left, and I believe is what she showed in her work. On the right-hand side, though, this is from our transverse velocities or cross-stream velocities. And we are actually seeing an inverse relationship here, which still baffles me. But I think this is kind of a feature of our channel in that we don't have independent control over, we can't control the depth really very well in this chapter. We can only control the discharge, and the depth kind of goes with it. This flume is still being modified. But we see a relationship, and even kind of with this funky behavior. On the right-hand side, we can see we have a pretty good match between our integral length scale measurements from the surface PIV, and this is across the whole channel width. You can see on the horizontal axis, and on the vertical we have our actual water depth. So putting this all together, I'm on my last couple slides, don't worry. We can put this together to see, can we calculate discharge? So from the surface PIV, we look at our turbulence, in this case the integral length scale. This gives us some measure of our depth. We know our width, so this gives us our cross-sectional area. From the ADV measurements, we can figure out our depth average velocity, and from that calculate our discharge Q. And then with that, compare that to the actual Weir discharge. We see we have a fairly wide array of Reynolds numbers, in my opinion. And then using those integral length scale measurements, how much variation did we have between what we calculate as our discharge and what we measure? 7% agreement, pretty good, 61% less. So there's a huge variability here, but we are still optimistic about this, maybe naively so, just as a cheap way of, if with an $800 camera, can we figure out just kind of how bad of data can we have and still get something that is practically useful in the field? We know that, yeah, these measurements are extremely dependent on our data quality, and it is hard to get good quality data outside in an uncontrolled environment. So we have a few things to try moving forward, trying different lenses and features, and then ultimately, if this goes well, adding artificial bathymetry and trying this in the creek. And I will end just to say thank you. My student on the left, Julio, is who did all this work. So happy to take a question if there's time, or I'll just watch the chat. Thank you.
Yeah, thank you very much for your interesting contribution.